Hello everybody, this is Mika Seppälä. In this podcast I present a number of solved problems on the definition of the derivative. The problems to be considered are the following. First, on the figure on the right, you can see graphs of two curves, a red curve and a blue curve, curve A and curve B. One is the graph of a function and the other one its derivative. Which is which. In the second problem, we will have to find out for which values of the variable x the function absolute value of x has a derivative. In the third problem, we have to compute the derivative of the function 1 divided by square root of x using the definition of the derivative. In the fourth problem, we have to find out whether the function x squared times absolute value of x has a derivative at x equals 0. And in the fifth and last problem, the same question for the function f of x, which is defined by setting f of x equals x times cosine of 1 over x when x is different from 0, and 0 when x is 0. Does this function have a derivative at x equals 0? We solve these problems by the definition of the derivative. I remind you that the derivative of a function f at x0 is the limit of f at x0 plus h minus f at x0 divided by h as h approaches 0. We of course assume that the limit exists and is finite, otherwise the function f does not have a derivative. We use this definition in the problems that follow. In the first problem, we consider two graphs, graph A, the red graph, and graph B, the blue graph. They are the graphs of a function and that of its derivative, and we have to figure out which is which. In the solution, we need to use the fact that the derivative gives the slope of the tangent line. Consider this interval from C to D. The red curve on that interval is decreasing. Therefore, any tangent line of the red curve on that interval has a negative slope. The blue curve, on the other hand, takes positive values on the interval from C to D, and hence we conclude that the blue curve cannot be the graph of the derivative of the red curve. Therefore, the graph B is the graph of the function, the blue graph is graph of the function, and the red graph, graph A, is the graph of its derivative. In this problem, we have to find out for which values of the variable x the function absolute value of x has a derivative. We have to find this out using the definition of the derivative. The derivative, if it exists, is the limit of, in this case, of absolute value of x plus h minus absolute value of x divided by h as h goes to 0. Now, if x is positive, then we may restrict ourselves to a situation where h is close to 0, then also x plus h is positive, and the absolute value of x plus h is x plus h itself, and the absolute value of x is x itself. So if x is positive, this limit of absolute value of x plus h minus absolute value of x divided by h is the same as the limit of x plus h minus x divided by h. Now here x cancels out, we get the limit of h divided by h. Now h divided by h is always 1, therefore also the limit is 1. We conclude that the function absolute value of x has a derivative when x is positive. If x is negative, we get precisely in the same way that the derivative of f exists and equals a negative 1. If x is 0, then we have to consider the expression f of f at 0 plus h minus f at 0 divided by h. And now if h is positive, then f at 0 plus h is h itself. So if f is positive, f at 0 plus h minus f at 0 is simply h divided by h, which is 1. If h is negative, then we get in the same way that f at 0 plus h is negative of h, because f at 0 plus h is the absolute value of 0 plus h, that is the absolute value of h, and if h is negative, the absolute value of h is negative of h. And therefore the expression f at 0 plus h minus f at 0 divided by h is negative h divided by h if h is negative. And this means that the expression f at 0 plus h minus f at 0 divided by h is 1 if h is positive and negative 1 if h is negative. And this means that this expression does not have a limit as h approaches 0. It does have one-sided limits, but the one-sided limits are 1 and negative 1, and they do not agree. Therefore, there is no limit, and we conclude that the function absolute value of x has no derivative for x equals 0 and has a derivative for x different from 0. In this problem, we have to find out whether the function g of x equals x squared times absolute value of x has a derivative at x equals 0. We have to compute by the definition. In the definition of the derivative, we have to take the limit as h approaches 0 of the expression g at 0 plus h minus g at 0 divided by h. You plug in place of g its definition. So g of h is h squared times absolute value of h. G at 0 is 0. So the whole expression becomes h squared times absolute value of h minus 0 divided by h. Now h cancels out and you get h times absolute value of h. And you conclude that the expression g at 0 plus h minus g at 0 divided by h has a limit 0 as h goes to 0. This means that the function g has derivative at x equals 0 and that the derivative is 0. Here on the right you see the graph of the function g, x squared times absolute value of x. Consider the function f of x defined by setting f of x equals x times cosine of 1 over x when x is different from 0 and 0 when x is 0. Does this function have a derivative at x equals 0? On the right you see the graph of this function. It oscillates wildly between the lines y equals x and y equals negative of x. It appears to have a limit at x equals 0. The limit seems to be 0, so the function is continuous. But now, to study the possible existence or not of the derivative, we must resort to the definition. Consider the function f of x defined by setting f of x equals x times cosine of 1 over x when x is different from 0 and 0 when x is 0. The question is, does this function have a derivative at x equals 0? We compute by the definition, and we consider the expression f at 0 plus h minus f at 0 divided by h. This expression must have a limit in order the function to have a derivative at 0. Now this expression becomes h times cosine of 1 over h minus 0 divided by h. H cancels out, so you get simply cosine of 1 over h. Now the function cosine of 1 over x oscillates infinitely often between negative 1 and 1 near x equals 0. Here you see the graph of this function. This function does not have a limit at x equals 0, and this means that the expression cosine of 1 over h does not have a limit as h approaches 0. So we have concluded by the previous observations that cosine of 1 over h does not have a limit as h approaches 0, and therefore the quantity f at 0 plus h minus f at 0 divided by h does not have a limit as h approaches 0. And this means that the function f does not have a derivative at x equals 0.